Hi, everybody. My name is Lori Diachin, and I'm at Lawrence Livermore National Lab and serving as the project director for the Exascale Computing Project. And today I'd like to tell you a little bit about our status as of April 5th, 2024. Technical work has completed, and so this will largely be a talk about the successes of ECP, some of the lessons we've learned, particularly around the topic of integration. Oops, sorry. So in terms of the bottom line up front, exascale systems have been successfully delivered. The Frontier system at Oak Ridge National Lab was delivered in 2022, and the ECP teams started to get access to it in October of that year. We had full access to it in April of 2023, and all of our application teams and our software technology teams were able to get onto the machine and really demonstrate the power of exascale computing in the overall high-performance computing ecosystem. Our applications were able to achieve factors of hundreds and sometimes even thousands of times performance improvements in their science work rate. So, real measures of how fast they're able to do science relative to their performance at the beginning of ECP, which was in 2016, when we had machines on the floor that were about 20 petaflops. I think another factor that's been really important in the exascale systems is one of the key metrics for success of the system was, can you do an exaflop within a constrained power bound? So one of the targets that the vendors were given was 20 megawatts per exaflop. When we first started looking at exascale computers, we were worried that the energy usage would be 500 megawatts or even more. And so having a target of getting it down to 20 megawatts per exaflop is a tremendous benefit, not only for high performance computing, but these kinds of energy savings can be seen across the high performance computing landscape, in academic centers, department centers, industry, high-performance computing, and even actually down into your laptops. Those sorts of energy gains will be something that we can all take advantage of at all levels of computing. I would say that the Exascale Computing Project was, one of the first out of the gate in using these types of high-performance graphical processing unit, GPU, type architectures, and the development of the applications and the strategies we use to make good advantage of those architectures, along with the significant investment in the software ecosystem that I'll talk about, that we have made available as open source, has significantly de-risked adoption of these kinds of technologies by other agencies such as NASA, DoD, NIH, and also industry. And so we'll talk a little bit about that later today. And I would just say that we already are seeing benefits for thousands of users in the applications, the software, and the exascale ecosystem that's been developed. So as I mentioned, the exascale capabilities, they're real, and they are deployed at DOE facilities. So the US is slated to receive 3 exascale computers. As I mentioned, Frontier was the first that was delivered at Oak Ridge National Lab in May of 2022. It achieved #1 status on the top 500 list, and it's currently listed at being able to achieve 1.19 exaflops on the LINPACK benchmark that's used for measuring performance of the systems. So the machine now is very stable. It's highly performant. All of our applications have been able to get on to the machine and run their applications at full scale. And it's really been an excellent performing machine. So far, that machine has delivered on 6 Gordon Bell and prizes and special prize finalists, which are awarded to some of the most interesting and high-performing applications at the Supercomputing Conference every year. The second system that is in the process of being stood up now is the Aurora system at Argonne National Lab. So the full system has been delivered to Argonne National Lab, and they've installed it as of June of 2023, and they're working now on the scaling phase. So these machines come with millions, and I mean, it's millions of parts. And so there are often some issues that we'll see when we're standing up a, serial number one machine. This machine is from Intel, so a different company from the Frontier machine, which was AMD. And so again, a lot of the same kinds of issues in standing up a number one machine are being worked through now. ECP had limited access starting in July of 2023 for some of our team members who are located at Argonne National Lab, and we received full access to the machine in November of 2023. Some of our teams have been able to run on about 2,500 nodes, and again, seeing excellent performance where they're able to achieve some of their science goals on even just a portion of the Aurora system. And then the final system that will be an Exascale system here in the US is being delivered now to Lawrence Livermore National Lab, and installation is underway even as I'm giving this presentation here in early April. This machine's expected to exceed 2 exaflops when it's deployed later in 2024. It's the same basic architecture as the Frontier system, just one generation later. And so there will be a brief period of open science for this machine as it's, again, being stood up and shaken out. But then it will transition to classified use for mission-focused work and stockpile stewardship for Lawrence Livermore Los Alamos and Sandia National Labs. So when we first stood up the Exascale Computing Project, there were a number of goals that the project overall was trying to reach in creating a capable software ecosystem. And so this was in 2015, 2016. At that time, there was a lot of concern about the efforts that were being made, particularly in the Asian community, such as China. And so we wanted to, for many different reasons, maintain leadership in high-performance computing within the U.S. And there are lots of reasons to do that. We've had international leadership for decades, and so we did want to maintain that leadership for our science goals, for our national security goals, etc. Another major goal was to promote the health of the U.S. high-performance computing industry. Again, at that time and even now, a lot of the computing needs are being driven by markets that are not high-performance computing. And so being able to invest in our vendors, such as Intel and AMD, IBM, NVIDIA, and having them focus on high-performance computing, it does have really great effect for the country overall as that technology then trickles down into the rest of the computing ecosystem. And then the two goals that were, very directly related to the software that was developed by ECP was in building and delivering a sustainable software ecosystem. So this is the mathematical libraries, the development tools, debugging tools, performance assessment tools, visualization tools that application developers need to get their job done and really have good insight into the science. So the idea here is to create an ecosystem that can be maintained for years to come. So future-proofing it, and we'll talk a little bit about that later in the presentation. And then finally, none of this is useful at all without the applications and being able to ensure that these systems can be used to deliver mission-critical applications in a very wide variety of areas. And again, we'll talk a little bit about the breadth of that application suite when we get there, but that was a key mission need for the Exascale Computing Project. And I'm happy to say that we've been able to deliver on all of our mission need statements for the US. So to introduce the Exascale Computing Project, just briefly, it's a very large project that's spread across many different institutions in order to create a management structure that allowed us to, create bite-sized chunks. We divided our technical work into 3 focus areas. One was application development, which was focused on 24 applications and 6 co-design centers that were tightly coupled with those applications, led by Andrew Siegel at Argonne and Eric Drager at Lawrence Livermore National Lab. And then software technologies, which again was looking at that sustainable software ecosystem that I just talked about. In particular, within ECP, we funded 70 different unique software products that spanned a wide range of different kinds of technologies that are needed by application scientists. And this was led by Mike Haru at Sandia National Labs and Lois Kerfman-McInnes at Argonne National Lab. And then we also had hardware and integration. So it was not the job of ECP to buy exascale systems and stand that up. That was the job of the DOE high-performance computing facilities at Oak Ridge, at Argonne, and at Lawrence Livermore. We did have a key dependency on those facilities. We couldn't do what we needed to do without really tight coupling and connection to those facilities. And so we stood up an entire work area that was really focused on initially delivering technologies and building technologies that would be useful in the exascale system. So we invested in 6 high-performance computing vendors through our Path Forward program to look at node systems, memory systems, interconnects, et cetera, to really get those ready for deployment in the exascale systems that we have today. But then also looking at the integration of our applications and our software technologies directly onto the facility hardware as it was being delivered, and managing that process in a way that was a win-win for ECP and for the facilities. And this effort was led by Richard Gerber at Lawrence Berkeley National Lab and Susan Coughlin at Argonne National Lab. So the Exascale Computing Project was the largest computing project in the history of the Department of Energy. So we started in 2016 with a budget of $1.8 billion that was to be spent over 7 years. And it funded over 81 different research projects in applications and software technologies and hardware and integration, with that funding being spread across most of the DOE labs, 15 of the 17 DOE labs, almost 60 university partners, and then nearly 40 industry organizations. And so it was a very unique opportunity and collaboration that brought together, this whole community, from the application developers to the software technology experts to the hardware experts from coast to coast, and set them on a single path to really to make the best use of these systems that we could. And because of that long-term collaboration over 7 years with this large-scale team, there are a number of things that we were able to do within ECP that we'd never been able to do before. And so there's a lot of best practices and lessons learned for how we manage the project, how you program, GPUs, that we are sharing now with the rest of the community, trying to move the entire nation forward in high-performance computing. So as I mentioned earlier, there are many different applications that we funded, and this chart just shows that breadth of the applications. It ranged from applications that were, again, already performing very well on petascale systems in 2016, in molecular dynamics, in lattice QCD, and other areas, to applications that really needed a lot of focused investment to get them ready to operate at the very highest scale. So for example, in the power grid space, there wasn't a lot of high performance computing that was used to model our power grid in 2016, and the ECP has changed that. So this just gives a nice overview of the breadth of those applications, ranging from basic science to things that really impact our economic security, our energy security, climate modeling. We have a collaboration with NIH that's focused in on cancer. So just a very, very wide range of different applications. So these 24 applications and 6 co-design centers really represented a pretty broad swatch of codes. So there's 62 different codes within these 24 applications, representing well over 10 million lines of software. A lot of them support very large user communities, have user bases of 10,000 or more. And almost all of them, when we began the project, were focused on MPI only, or maybe a mix of MPI plus OpenMP, mostly on CPUs. So there were a few machines that had GPUs at the beginning of ECP, but it was not yet kind of that dominant factor in the high performance computing landscape. So a lot of our applications had a long way to go to get from where they started to where they ended. And so, as I mentioned earlier, applications were evaluated in one of two categories. For those that were already working well on the 20 petaflop machines in 2016, they needed to achieve a performance increase of about 50x and do a science challenge problem that was simply infeasible on the machines of 2016. And then we had capability applications that did not need to meet that performance goal because they didn't have a baseline. They didn't have codes that were really operating at that level. But we did want to expand the reach of exascale computing. And so they were charged with, dreaming up, what is a science challenge problem that could use an exascale machine that we can't do today and that could make good use of the architectures when they're delivered. And so we measured our success through these key performance parameters. Two were around the applications that I just talked about. So KPP1 is that 50x performance improvement. We had 11 applications that were in this category. And at the end of ECP, we had 10 that were able to complete that goal and achieve over 50x. We did have one application that unfortunately hit a nasty bug. We think that they will be successful in the long run, but they're still working through the debugging process of running on a machine at the scale, a first of its kind machine. For KPP2, these are the ones that were not yet ready at the beginning of ECP to run on high performance systems. We had 14 applications, 10 in DOE's Office of Science and 4 in the National Nuclear Security Administration, or NNSA. And so of those, 9 of the Office of Science applications and 3 out of 4 of the NNSA applications were able to demonstrate good use of the GPU architecture and that they were able to develop all the needed physics capabilities for their challenge problems. I talked a little bit about integration as one of our key goals in developing this software ecosystem. That was measured by our third key performance parameter, where we had 76 unique software and co-design products that we tasked with achieving at least 4, maybe 8 sustainable integrations with a client environment, where a client could be an application code, another software technology, it could be deployment on one of the facilities. And we added all of those integrations up in a weighted average so that those that had more impact had a little bit more weight than those that were a little bit more on the risk mitigation side, for a total of 68 possible total points. And our goal was to hit 34, so a 50% mark on that weighted integration score. And we've had tremendous success here. So we've managed to hit 63.5 integration points, and we actually still have 3 that are completing the review process with the subject matter experts. And so we expect to hit 66.5 out of 68 possible points. And then finally, KPP4 was around the development of those technologies that were going to be needed for the exascale systems. So these were around the milestones that were part of our Path Forward program, which funded the vendors, IBM, NVIDIA, AMD, et cetera, Intel, to develop these technologies. And our goal was that if they met 80% of those 267 milestones, it was highly likely that there would be exascale capabilities that would be deployed with the machines that we're seeing today. So this KPP closed out actually several years ago, and the vendors did meet 100% of those milestones, and we are seeing some of those technologies impacting the exascale systems that we got today. So I think one of the most amazing things that we've seen is how much the projects have surpassed our goals. So when we first laid out a 50x performance target for our applications, we thought that was really ambitious because, as I said, many of the applications had not really used GPUs. We didn't know what architectures were coming. We didn't know what the software stack was going to be. And so setting it at a 50x performance target, which means that they're making, perfect use of the increase in performance in the hardware, was risky. And so we did have, our moments when we wondered, are we going to meet this goal? And I mean, now looking back, we're like, yes, not only did we meet the goal, we surpassed it, but I don't want to take away from the fact that it was an ambitious goal when we set it. So this is a logarithmic scale. And this gray line that you see is the 50x performance bar that we set for these applications. And you can see that many of them, have gotten over the 50x, maybe to around 70 or 80, but a lot of them have reached, 200 or 300x the performance. And EQSIM was able to adopt a number of algorithmic improvements that allowed it to achieve over 3,000 times the performance it had in 2016. And so I do want to emphasize that this, just outstanding result has been a combination of the improvements in the hardware and leveraging this highly efficient, highly performant hardware, but also changes in algorithms that allowed the teams through, long collaborations with mathematicians and computer scientists to make even more advance than we thought would even be possible. So it's a very exciting result that's allowing science to happen that wouldn't have otherwise been possible. And as I've been mentioning, this would not have been possible without the software stack that we've developed. So I do want to take a few words here to mention E4S. So that's our extreme scale scientific software stack. And this is the software ecosystem that the ECP has built that now has well over 115 products that are part of its quarterly releases. So not only does it contain all 70 of the 76 of the software products and co-design center products within ECP, there have been outside entities that want to be a part of E4S and a part of this ecosystem that have also decided to become, basically a part of this family. And so what does this provide for the broader community? Basically, it provides infrastructure and community policies so that if you are using part of E4S, that it's been highly curated, that it's been tested, where you can find the documentation, where you can get help. And so that really de-risks for a lot of folks this idea of adopting external packages, which can be difficult to, build, or when versions change, all of a sudden there's a lot of issues with compatibility across the software stack. E4S takes care of all of that. And so this, we think, is going to be one of the longest lasting legacies for the ECP going forward. And I want to highlight and emphasize that one of the most important strategies to ensure this robustness of E4S, which is built on these software development toolkits or SDKs, was this multi-layer testing framework so that when you use one product within E4S, that it is compatible with and will work well with the other products that are a part of that release strategy. And so we've spent a lot of time developing these testing strategies with our individual products and what the requirements are for each individual product to be a part of E4S, testing the interface between different libraries that are intended to work together from a functionality perspective, not just be built together, but actually work together. And then subsets of interoperable packages, and then, the whole SDK or E4S at one level. And because it's tested as a complete unit, and it all works together, that if you choose any subset of these packages, then those will also compile and work well together. And again, that's a huge burden that is lifted from application teams. So there are lots of integration examples. We had over 290 successful integrations of ECP software technologies into the applications. There are a couple that I can highlight here just quickly, related to, linear algebra and solver performance, discretization libraries, adaptive mesh data structures, FFTs, et cetera. So I encourage you to peruse our websites and our other recorded presentations to get deeper dive examples of the kinds of integrations that were performed. So I think one of the big success stories was one of our co-design centers, AMREX. So this was focused on structured adaptive mesh refinement, and this turned out to be a real nexus of integration. So not only were there a large number of applications that were building on top of AMREX, from combustion codes to wind codes, cosmology codes. It also served as an integration with some of the underlying libraries that are really critical, such as nonlinear solvers or algebraic multigrid type libraries or data and analysis tools. And it was through AMREX that these applications could get access to some of these other technologies. And of course, all of this was available through E4S and could be built using SPAC recipes. And so it was just a really nice example of a nexus of integrations that has worked well for many applications. For Exawind, their objective was to really create ground truth simulations that looked at modeling multiple turbines in a complex topography for the siting and operational control of wind plants. So they developed a brand new capability that was based on advanced solvers, advanced discretization schemes, adaptive mesh refinement, just a wide variety of different technologies in order to achieve their goal of modeling, as you can see here, 4 turbines in 3 dimensions. You can see the wake fields interacting with each other, which can significantly impact the performance of wind farms. And just recently, this team used these very high resolution, high fidelity simulations to train a machine learning surrogate model so that it can be deployed and delivered to engineering scale code. So it can run very, very quickly, but still get the kinds of accuracies that you can see with these high simulation codes. So this has just been a really great example of the use of a lot of different applied mathematics libraries, solver technologies, in order to achieve this goal of these high fidelity wind solvers. And then the final example I'll highlight here is looking at small modular reactors. And so in this particular case, there were 2 aspects to this. So there were Monte Carlo neutron transports, which tracked particles through the reactor bed, and then high performance fluid dynamics that looked at the turbulence associated with the fuel stack. And so a couple of things had to happen here. When they initially put the particle tracing algorithms on the GPUs, they performed far worse than they did on CPUs because GPUs are not so great with branching. So there was a lot of, when you're tracking on a particle by particle basis, if something happens to this particle, then it does this. If something else happens, then it does that. So that sort of decision logic does not work well on GPUs. So what they did instead was they flipped the whole algorithm on its head, and they looked at the whole problem from the perspective of, for all particles that are undergoing this type of an event, a collision or whatever it is, do the operations in a very fast and efficient way. And by flipping it on its head, they were able to get much higher speed than they were previously. And so that was a tremendous advance for the neutron transport codes. For the computational fluid dynamics, they really started to focus in on very high order accurate discretization schemes, which again, pack a lot more math, a lot more operations into the GPUs per memory access. And so able to get a lot more utilization out of the processing unit than they could previously. And so this allowed the teams to really enable these simulations in just unprecedented in ways. So when the project started, these teams were able to look at the initial state of the reactor bed, and that was it. With our systems that were available in like the 2020 timeframe, those that were operating 100 to 200 petaflops, they were able to take snapshots in time later when there were different kinds of ions and other more complicated dynamics in the fuel bed that allowed them to take snapshots. And what they can do now is a time history from the initiation of the fuel, through time, and see the evolution of how that fuel bed's reacting. And so this was one of our finalists, these simulations on Frontier for the Gordon Bell Prize in 2023. So we had a lot of mechanisms that we used to encourage these really significant interactions between AD and co-design and ST teams that were really important in terms of, you can't force these sort of collaborations, but you can incentivize them through constructs such as shared fate milestones and the annual meetings that we had where everybody came together, all the application teams, all the software technology teams, to share ideas and to share the lessons that they had been learning along the way. And then the long time horizons that we had, the 7 years for this project, really allowed the teams to dive deep and really get to know what the problems were. And it's astonishing the kinds of innovation you have when you have that sort of stable funding over a long period of time. So I want to talk a little bit about how we measured what we valued, and then the integration that the tools that we use to really develop these tight couplings and integrations across the project. So, measuring what you value. So this is about that KPP3 that I mentioned earlier. Those sustainable capability integrations were how the ST teams were measured for success. And that really incentivized them to reach out to the application teams and really try to get their products in use in a sustainable way. Again, in the applications, in other software technologies deployed on the systems. And so that was a key aspect of ensuring that integration happened within ECP. So as I mentioned earlier, we completed 290 substantial integrations on the Exascale systems as part of KPP3. We had different types of integrations that you could choose, direct client integration, which is broken down further here by application development team, by other software technology teams, by co-design centers. You could be integrated into a community standard. We did a lot of work with OpenMP and MPI and other community standards, deployment at the leadership class facilities, and then usage of tools. And so this bar chart here just shows that sort of a histogram of these integrations as they were completed and measured over time. So, getting to our, weighted integration of 38 here, you can just see what that progress was over time. So this did require a lot of attention within ECP, both for our internal dependencies between AD, ST, and HI, but also for the external dependencies that we had with the facilities, with the vendors, and with our open source software. And I want to spend just a few minutes talking about how we managed this and the kinds of tools that we used. So there are many different mechanisms that we use to manage these integrations. So it ranged from project management constructs. So we just talked a little bit about KPP3 and how that was a project management construct that really encouraged this integration. We talked about the shared fate milestones to track engagements between AD and ST, but we also use them to track our facility engagements. We developed engagement plans with the leadership class computing facilities and funded scope with facility staff to work on ECP projects and have them work directly with the teams. Other key avenues for managing integration were the communication tools that we used, and then the project management tools that we had. So in terms of communication, there was a lot of different aspects that we used, and I'll talk about some of these going forward. And then, tools that are useful across all 1,000 members of our team to look at JIRA, to, understand various different dashboards, et cetera. So these are the kinds of technologies that we have mentioned or will mention briefly in the next few minutes of the presentation. So one of the critical mechanisms that we had was the ECP dependency database. So because there were so many application teams and so many software technology teams, it was very hard to track who was using what, who needed it, in a critical way. There were no alternatives. What was the time frame for when that would be needed? And so we built a database that allowed us to very explicitly, look at this and understand at a deep level who depended on what. And so you can see here an image of, these are some of our application codes, and each one of them had to go into the database and indicate, what am I critically dependent on? That would be the red bars. What's really important to me? That would be the blue bars. And then what am I interested in? And, maybe, I don't need it to succeed in my job, but I'd really like to try it out. And so you can see that almost all of our teams had some sort of critical dependency, and many of them had important dependencies. So these were clickable, so you could go into the dashboard, click on it, it would open up a separate window, and you could, look down and see exactly what each team was dependent on and in what way it was dependent. So this was used for a lot of analysis of the key ST products that were going to be needed for AD applications and when they would need to be deployed, understanding which teams had lots of dependencies on ST products so that we could track that, and then lots of communication actually with the vendors and facilities about what was critical and what would be needed when. So this turned out to be an incredibly useful tool throughout the life of the project. Another thing we did to track and manage our dependencies was our risk register. So we had a very formal risk register, and about 75% of our risks were related to dependencies. So we had a number of dependencies that were related to facilities and the vendors. So getting access to the systems in a timely way so that we could do our development and our testing. A lot of our software stack leveraged and complemented what was happening at the facility and at the vendor. And so we had to explicitly track those interactions to ensure that there weren't going to be any gaps there. Internal dependencies, for AD to meet its goal, the ST technologies had to perform well. And so this was a risk we explicitly tracked generally, but we also called out, key products very specifically, such as MPICH, OpenMP, some of the linear solvers, and then making sure that they were successfully deployed at the facilities in a very sustainable way. And then finally, we did have a heavy reliance on open standards such as MPI and OpenMP, and there was some risk associated with that where we were trying to influence these standards to make sure they were operating in a performant way for our needs and in our time frame. We instituted monthly integration meetings to provide a forum for these discussions. So these started in April of 2019. So we were about, 2.5 years into the project at that point. And the goal initially was just to sort of resolve the inconsistencies and to establish this clear picture of where we were. So from this discussion came the integration database that I just talked about. But there were lots of very timely discussions that we had around continuous integration and early experiences on some of the early access systems and the test and development systems. One of our challenges was sharing information that was deemed proprietary by the vendors. And so how can we manage that and share that information? And so as the project went along, we actually started to combine that with our monthly risk meeting and talked about risk and integration as a collective because they were so deeply intertwined. So this turned out just to be a great communication mechanism that gave us a forum to focus on these topics very specifically. So I'll just wrap up by saying, it's not just the Exascale machines that are leadership class, so are the ECP technologies and the participants. So, this is just an example of, many of the ways in which ECP technologies and people have been recognized over the years. So again, this represents the years of the project. Of course, many of these awards are based on work that happened prior to the ECP, but it just shows the quality of the work that we were funding in terms of R&D 100 awards and people to watch and the team that we were funding. The Gordon Bell finalists, Jack's AM Turing Award in 2021, was a very nice recognition for just a real leader in our community who was an integral part of ECP. And there are just many more examples of this, in lots of different forums and with different professional societies. So we're capturing and sharing our lessons learned. There's a lot of things that we've learned on the technical side regarding performance portability, the strategies for moving from GPU accelerated to GPU resident, how you manage when you're facing an inflection point in the hardware, and the fact that software really has to be a first-class citizen in terms of the investment. Lessons learned around collaboration, and we already talked about a number of these in terms of incentivizing collaboration and building in integration into how you measure success. And then lessons learned around project management. Haven't spoken about it a great deal in this presentation, but we were managed in a very formal way because of the size of ECP by the Department of Energy. And so that required a lot of very formal constructs that we had to tailor to ensure that it worked well for a research and development team like the ECP was, managing our dependencies, having the centralized project management tools. We used a lot of the Atlassian tool suite to provide a centralized avenue for sharing information, and that just worked out really well for our project. And these, I think, are things that can be leveraged and used for projects at many different scales, not just at the scale of ECP. So we're working now to spread the word. We're in our final phase of the project. We've completed technical work as of most of the technical work as of December 31st. And there were a few projects that extended to March 31st to demonstrate the utility of artificial intelligence on exascale resources and just the power that bringing those two things together can yield. So we're looking at our integration case studies, some of our then and now articles. Where did these applications start, and then where did they end up, and what was the tremendous progress that they made? We're working on a couple of different books around our lessons learned and the story of the Exascale Computing Project. Had a lot of presence at SC23, at the SIAM Parallel Processing meeting this past spring. And we continue to work with our industry and agency council to spotlight articles on how they've been able to take advantage of and leverage ECP technologies. And speaking of our industry and agency council, we have been very active with this group. You can see here that there are a large number of very well-known large corporations that are using high-performance computing as part of how they get their work done and deliver their products. And so we have been meeting with them since the beginning of ECP. And just in the, this is just showing example activities in the last year, where we did a deep dive with NASA on how NASA could leverage both application technologies and software technologies. We've had focused workshops on topics such as continuous integration, and there was one on Fortran earlier, and just a number of different topics. We had a panel at SC23 that was run by Fran Hill at the Department of Defense, where she brought in a number of our members to talk about the impact of exascale on industry and what does that look like. And there are many great examples of how technologies that we've developed within ECP are being much more widely used and impactful. So we think exascale computing will have far-reaching consequences for the community. It is real. It's delivering just remarkable science. But it's just the start. We're only at the very beginning of the exascale era. And effectively utilizing these kinds of GPU, CPU architectures, we think has really changed the landscape for the better. And there are lots of ways in which we see this. We already talked about the performance improvements that are possible in your science work rates when you shift and take advantage of the GPUs. And so just even, imagine how 100x performance can impact different industries, different science goals, different national security goals, and those goals can become very widespread because it's not just at the exascale, it's at all levels of computing that we can see these improvements. I think another major win for everyone is this energy consumption. I mentioned it at the beginning of the presentation that a real goal was getting the power envelope down to, an exaflop in 20 megawatts. So that then trickles down to the rest of the computing ecosystem. There are many centers, at universities and in industry that are constrained by their power and how much power is coming into their compute centers. So being able to leverage much more compute power for the energy that they have is just a big win. And it's also more sustainable, just from an energy consumption perspective for the United States. And then the applications and the software that I've talked about throughout this presentation, they already have a large user base. They're being used by tens of thousands of users. And so those gains have already made their way out into the science community. And so with that, I'd like to say thank you for your time and your attention to this presentation. I do want to thank the entire ECP team. I mean, this is clearly not my work. This was a team of 1,000 researchers and a strong leadership group. And so, this work just really represents the creative contributions of many people who were thrilled to be a part of the Exascale Computing Project. So I want to thank our sponsors with DOE's Office of Science and the National Nuclear Security Administration for really giving us this opportunity to deliver on the next generation of computational science.